So this is the last session. The moderator for the session is going to be Professor Eric Darve. Professor Darve has been at Stanford for several years. He's in mechanical engineering and one of the founding members of ICME, very much involved with the activity of the institute and for many years from the very beginning. So, Eric?
All right, so I'm going to start with just a short introduction. So the topic for this session is physics AI. And so, obviously AI and machine learning has been very successful in computer science for many applications, computer vision, image processing, natural language processing, and so on. And so, during the last 5-10 years, it's made some inroads in physics and engineering. So one of the main, I guess, differences with sort of more computer science applications is the availability and source of data. So for physics, it primarily comes from either experimental data, and so now we have widely available sensors and high-throughput experiments that can generate large amounts of data in sort of an automated fashion. And obviously, we've developed across several decades, many PD solvers or solvers for, complex physics models that can, produce large amounts of data. And so this is sort of a fertile ground to build some of these AI models. So I've sort of highlighted some of the areas of applications or sort of success stories for AI for physics. So first you have learning from physics and data. So I guess during the last sort of decades, learning was mostly done in terms of PDEs, applying physical laws, conservation laws, physical principles, and so on. So now with this data, there's this push to learn both from this traditional physics and also from data experiments or high-fidelity simulations. So in the area of uncertainty and probabilistic modeling, so for example, this is one area that was traditionally sort of dominated by certain types of approximations like Gaussian models and linear maps. And so with machine learning, we have new techniques like generative models and, of course, nonlinear maps through deep neural networks that have allowed expanding the areas of applications of these uncertainty and probabilistic models. So next area is high-dimensional circuit modeling. And so, for example, again, in the area of PD solvers, traditionally, we've been limited to typically like a 3D or 4D setting, so like spatial dimensions, where you can do finite element or Cartesian grid and so on. And there's been some methods to deal with high-dimensional problems, like sparse grid and maybe radial basis function interpolation. But to a large extent, this high-dimensional interpolation problem or regression was largely ignored because of the difficulty of high-dimensional regression interpolation. But again, for example, deep neural networks have shown great capacity and robustness and accuracy for high-dimensional regression, and so this has opened a lot of new avenues in applying these AI methods for physics. And finally, there's a lot of techniques, for example, in reinforcement learning and similar techniques that come from machine learning that people have started applying to physics problems, and so we'll hear more about this in one of our sessions. So these are sort of some of the buzzwords or sort of areas of applications of machine learning in engineering. So the first one that you've probably heard about is physics-informed learning, which is basically, again, this idea of bridging data and physical models. So traditionally, everything was physics-based in engineering. I guess techniques in computer science and statistics are primarily data-driven. So there is, a unique opportunity of sort of trying to bridge these two areas for engineering applications. So I mentioned generative models. So generative adversarial networks, again, which have been very successful to model stochastic processes and to understand to quantify uncertainty in engineering predictions and also to build reduced order modeling. Then in the context of building surrogate modeling, so building low fidelity models that are computationally much cheaper, there's been a lot of applications of, for example, neural differential equations and graph deep neural networks that allow building coarse grain models at a fraction of the computational cost, and that can be trained from data. Anomaly detection is also another sort of powerful technique that has had a lot of successes in physics application, in particular in high energy physics that we'll hear about. So you have large-scale experiments that can produce petabytes of data, and you're looking for kind of unique, interesting events, like unique observations in these large-scale experiments. And so anomaly detection is, allows kind of automating this type of detection. And finally, I mentioned optimization, reinforcement learning, and control. So you may have heard about AlphaGo, for example, where an algorithm for reinforcement learning, has been able to learn very high-level sort of strategies in board games and games like Go and so on. And so similar techniques can be applied to optimize complex engineering systems. All right, so just a very brief introduction for our speakers. So our first speakers will be Kazuhiro Terao from Slack. And he's been applying machine learning techniques to process and interpret these very large data sets from high physics experiments. So you may have heard, for example, that machine learning algorithms have been sort of key tools for the discovery of the Higgs boson. And so these techniques have become very popular in high energy physics. So our second speaker will be Christiane. She has worked on applying reinforcement learning techniques, so optimization control for various renewable energy systems, including wind farms, and also for temperature control in buildings, so for heating and cooling. And our last speaker for this afternoon will be Dhruv Patel, who's applied machine learning methods to construct multi-fidelity techniques for various applications, including transport, fluid mechanics, and combustion. And so just as a way of opening this session then, what about physics for AI? So is it just a temporary fad that will go away after the excitement fades, or is it a more long-term revolutionary advance that will allow us to solve problems that were intractable before? And so hopefully, we'll figure this out. All right, thank you. Yeah, so our first speaker then will be Kazuhiro Terao. He's a staff scientist at Slack. And we'll talk about machine learning and AI at the frontiers of high energy physics at Slack. So Slack is the Stanford Linear Accelerator, so it's just next door. All right, thank you very much.
Yeah, thank you. So yeah, hello. I come from Slack. I work at Slack. So I talk about high energy physics, and I would assume for most of you that's just an alien name. You never heard of it probably. It's basically, so yeah, I start from there. So what is high energy physics? It's a combination of two things, two other alien words, cosmology. Well, cosmology probably people know, right? Basically, we look at the sky and think about how the universe has evolved to this point. And the other thing is particle physics. These are kind of two, to some extent, it's two opposite things. One thing, cosmology is, like I just said, what you imagine. It's you look at the sky and try to understand how how this universe looks like and why we have this universe at this state. So that's kind of like the picture on the right-hand side on that screen. And then you have particle physics. Particle physics is actually looking at the smallest scale. So we're looking for the most fundamental constituents in this universe. Right, so everything, for example, you see in the periodic table. Everybody knows periodic table. That's made of protons and neutrons. All the nucleus made of protons and neutrons. Only two types of particles. Proton and neutrons, they're also made up of electron, up quark, down quark. So those are even smaller particles. And the fundamental particles, what we mean by is something that cannot be broken down. Right? So it's a point particle. It doesn't have a sense of space. Right? And we try to basically, particle physics is an area of study. We try to explain the whole universe if possible. from the most fundamental blocks. And the cosmology is the other way around. Let's look at the big picture, big structure, and try to understand how this big structure emerged. But those two things, both of them combine in high-energy physics. So in cosmology, we use, say, telescopes, right? You look at the big sky, and your target object is very big, and your sensor is very small in that sense. And you try to scan the whole space. Particle physics is kind of opposite again, because you're looking at the most, the smallest constituents, like the most fundamental constituents in the universe, right? So you're looking at things that 10 to the minus 15 meter. That's like nucleus, and even smaller because we're looking at something that's inside nucleus, right? But we use a huge detector with respect to that, because like I said, it's a single atom you look at, inside the atom you look at, but the detector itself is like many meters wide. Okay, so those are the kind of things we do in the high-energy physics. We use those kind of two ends of the detectors, right? One detector is very big, looking at the very small things. One thing is very small, looking at the huge things, like whole universe. But the analysis technique is to some extent similar. It's same for any science. You make hypothesis, take data, compare against your hypothesis, and then derive your conclusion. Maybe your hypothesis is correct, or maybe it's incorrect. If it's incorrect in what way? So you can improve your model, right? So that's what I try to show it on this slide. The bottom left-hand side, you see you have some nature that has the physics in it, right? And then we do some experiments to take data from this physics, so from this nature. And then that shows up in some projection. If I use the imaging detector to look at the trajectory of particles, that's what you see on that over there with blue background color. You see a bunch of lines. Those are trajectory of some of the fundamental particles, and from these shapes, for example, or the color scale tells you how much of, what is the energy of this particle. From these behaviors, we try to infer what is the physics behind these particles and try to understand how this nature works. Now, on the other hand, we have also, right, decades or 10 centuries long understanding of how how this world works. So that's physics. So based on our physics model, we have our understanding of how these things should look like. And then we also have, okay, so that's what we want to learn, right? Or we have the hypothesis for. But then we have to transfer that information to compare against the data measured. So that means we have to think about experiment in aspect. What is the detector we use? So therefore, how the data should look like if I have this model. And then you have simulated data, for example, and you can compare the measured data versus simulated data, and then decide, okay, I think this part of the model is correct, this part of the model is incorrect. How should I improve this model? So that basically you do the hypothesis comparison in some 1D histogram or 2D, some, a few dimensional histograms, comparing again your model versus data, but it's projected in the experimental space. That's kind of how it works. I haven't talked about applications yet, but I think I spent half time. So what's unique about high-energy physics science? I'm going to introduce some of the machine learning techniques that we use, what kind of things we do with. But I think instead of talking about, I'm going to talk about them. But I think it's probably important or interesting to know what is unique about it, right? So I think I just picked 3 things. I'm sure there are more things, but 3 things that I usually talk about, okay, is first of all, the detectors, right? We have the kind of data. We have big data. Typically, it's multimodal because for the same information, we use different kind of sensors to look at the same physics information. Those sensors capture different information. So it's a little bit different from in terms of, like, say, image versus caption, because image versus caption, you usually look at the same thing in a different context. In physics, we usually look at, you don't want to pay taxpayers money for looking at the same information. So we actually use the detectors that look at orthogonal information. So that's what I mean by multimodal. As the introduction mentioned about it, it's a huge amount of data we look at. Typically, it's a high precision detector. Okay? So that means your data can be, for example, in the previous image, your data can be mostly empty. In that picture you see, right, I said lines are important information. That tells me the particle trajectory. But most of the pixels, they're just blue background, right? So from the big picture, the data is almost empty. But where we care about, it's very densely sampled. Another thing unique about, I think, physics is there's a very good understanding of physics models underneath. So it's not like we just take the data and try to make hypotheses. We pretty much have a very good understanding of how this detector works. What is the physics behind, what is the physics about the nucleus, right? Or atoms or nucleus. Those things we understand very well. How about if you go to even smaller level? What are the new physics? When you find a new physics, that has to, right, that information has to be consistent with everything you knew, right, everything you learned from the last centuries of physics. And so that's what I mean by there's a very good understanding, hierarchical models of physics that you have to satisfy when you make a new hypothesis. Finally, I think another kind of unique thing that when I interact with other people from different science fields is we have a very high fidelity simulation. So which is a tool you can use to explore the phase space to look for more information. Okay. So I just show you some pictures of what kind of data we take. So this is just another way of looking at the particle trajectories using a big imaging detector. Each pixel here is about millimeters, and then we're looking at the particle trajectories that's like many meters long. Okay, so you can kind of imagine how many samples we have. But again, in this picture also, most of the pixels are empty, so it's useless. This is just another kind of detector. In here, we're looking at the, you can see there's a bunch of lines, right? So there are about 10,000 to 100,000 of these lines, each of them about meters long. Again, you use a detector that can sample millimeter scale of these particles, trajectories, and then we measure different information, such as how long this trajectory is, what is the momentum, what is the energy of this particle, how much charge it's carrying. These information are measured by different kind of detectors, and you have to combine them when you analyze and infer physics. This is an example. I'm not going to go too much of details because actually you see some poster over there by one of our students. So I'm not going to go into too much details, but basically here's an example of how we use typical computer vision techniques like convolutional neural network to analyze the input data. So input data on the left-hand side, bunch of these colors, it's actually color scale means the energy deposition. But that's the raw data you can imagine. Right-hand side, we try to infer things like different kind of particles you're trying to classify. Maybe position of the particle endpoints, let's say regression problem. So these things you analyze so that you can understand about this particle. So the convolutional neural network is very well used, obviously, for the image data. We also use graph models. Obviously, I'm rushing. Graph models to analyze relational information, like where this particle came from, because there are certain physics laws that says this particle can only be produced from the decay of particle type B or particle type C. So you want to enforce these laws and analyze relational information between particles. So those things we use graph neural networks or graph models. I just spent maybe 1 minute to discuss about other kind of applications other than just doing the physics analysis with deep neural network. Other things is simulation. Like I said, we have a very good simulation model, right? So we use simulation for, these days we actually use simulator, let me say innovative simulator to do things like unfold the physics effect that we are not interested in. For example, experimental physics effect. I don't care about how detector works because what I'm looking for is fundamental physics, right? So can I undo detector physics? Estimate some nuisance parameter about this physics, and so on and so forth. So those are things we use with simulator. So in short, I assume most of you are familiar with computational techniques. So you can apply things like gradient-based optimization. You can do explicit gradient calculation or approximate gradient calculation. So we do lots of development like making physics simulation software differentiable, or use some surrogate model that can learn the derivative surface accurately so you can use to solve the differential equations. So I'm gonna skip this unfortunately, but it's basically what I'm saying is some inverse problem solving we also do with imaging. So there I leave because I already half minute passed. But yeah, so other things I didn't touch. I'm happy to answer if you have some questions. Even if I didn't talk about it, feel free to ask me when I'm in the panel discussion.
All right, awesome. Yeah, thanks for the presentation. So obviously, it's very hard to, they have big teams and a lot of research output at Slack, so it's very hard to compress everything in just 9 minutes. But anyway, we'll have the panel after these presentations, so you can maybe remember your questions and discuss that. All right. So second speaker is Christiane, and she is going to talk about applications of machine learning for control of buildings. All right. Thank you.
Thank you. When I talk about control of buildings, I'm talking about physical buildings like the one we're standing in now, or the residential buildings that you can see here. You can break up these buildings into a model. For example, the image on the right shows a single building split up into 5 different zones. For our control problem, we talk about having a state xt, which could be the temperature in each of these 5 zones. We also have some exogenous data, wt, which could be the temperature outside of the building. And what we want to do in control is take some action, ut, to achieve an objective. Our action could be cooling air in a central system and then applying power to fans to distribute that cool air to each of these zones. And the goal then is to minimize some cost, C of xt ut, for example, the energy cost of cooling the building, subject to some constraints. For example, we want our zone temperatures, the next time step into the future, to still be a comfortable temperature for the residents of the building. And we get that next time step from dynamics. The dynamics F take the current state and exogenous data, and then tell us when we apply an action, what is that next state. In reality, this dynamics model is incredibly complicated. We need to describe the full dynamics of heat transfer, of movement in a building. So typically, we don't have the true dynamics. We instead have some model. For a single time step, our control problem looks like this. We have the first state, x1, exogenous data, w1, and then we try to minimize the cost of that state x1, w1 when we take control action u1, such that our next state is still in our domain x, and that our next state comes from the dynamics. Solving this problem gives us one control action, u1, which we can apply to see what the next state is of our system. And we can call this problem just p of 1. In reality, typically we want to control over multiple time steps, say several hours or several days. So we solve not this control problem p1, but we instead extend it to control problem over big T time steps, p of t. We still start in state x1, but now we have exogenous data, w1, w2, all the way through wt, and solving this problem gives us a full set of control actions, u1, u2, all the way through ut, which we can apply to get our state all the way until t plus 1 time steps in the future. Before I dive into applying machine learning to this problem, I want to motivate it by looking at a learning-free approach called model predictive control, MPC. This approach is model-based, meaning, like I said before, we don't have those true dynamics. Instead, we have a model. If we were to solve the problem I just described, P of t with our model, as we apply that model after time step and time step, because there's error in our model, we also accumulate error in our prediction of the control action and its cost. So instead, we solve our control problem over a shorter horizon. Rather than the full control horizon t, we solve over a look-ahead horizon h, which is shorter than that full control horizon. The central part of this box here, that's the same control problem I just showed, but we're only solving it over for p of h, for that look-ahead horizon, and that gives us a final state, say 1 time step in the future, and we can then solve this problem repeatedly to get all of our control actions. MPC is used very widely and can be very successful, but it does have some challenges. One of the challenges is that you often need a large look-ahead horizon h for accurate control, and this translates into having to solve a very slow online optimization problem, which hinders real-time control. We can understand this by thinking about the building circumstance. With demand response pricing, you can often have a higher electricity price, say in the afternoon, when there's a lot of demand for electricity. Ideally, you would pre-cool the building before you reach that afternoon. However, MPC can only do this if it has a large enough look-ahead horizon to see that that peak pricing is coming. Another challenge of MPC is that you need to develop this dynamics model, which requires expertise and time. For building control, you need to modify some basic model for every new building you apply it to. The motivation then is, can we use machine learning to fix these problems? One machine learning approach is reinforcement learning. This approach is model-free, meaning you don't have a model of your dynamics. Instead, you figure out what your next state is going to be by taking measurements on your real system. Another difference from MPC is that you get your control action not by solving an online optimization problem, but from a policy, which is some simple set of equations that you learn, and that takes your state and exogenous data and gives you a control action. You get this policy by exploration. The idea of that is that you start in some state, xt, with exogenous data, wt, and then with some probability, you take the control action that your policy tells you to take. And with 1 minus that probability, you take a random control action to keep checking if there's a better control action you could be taking. You apply that control to your system and then measure what your new state is and what the cost of taking that action is. Based on that cost, you update the policy to decrease the future cost. You take your new state and you keep repeating this until you learn a good policy. By revisiting our MPC challenges, we see that that first challenge, that we have a slow online optimization problem, is solved by reinforcement learning. We're not doing online optimization anymore. We're doing offline optimization, and then when we're actually doing control, we just use our policy, which is quick. We also address the MPC challenge of needing to develop a physics-based model, at least to some extent. In what I just presented, there was no physics model in there. However, in reality, when you're training your policy, You don't want to be training it on a real physical system. For example, you might end up with really high energy cost or uncomfortable temperature. You might even break your central cooling system or your fans. So in reality, you do still need a model to train your policy on. Reinforcement learning also introduces some new challenges. It can require lots of data and time to train, which is a slow offline optimization problem. It can also be hard to interpret. In the building control example, if your temperature constraints aren't satisfied or your energy cost is high, it's hard to point to exactly why that happened. This raises a new question, which is whether we can combine MPC and reinforcement learning to overcome each of these challenges. One approach is MPC with a learned terminal penalty. That's this C theta. And if we look at the image on the top, which is the one time step MPC control problem, all I've done is add this penalty into the cost term, C theta, of the new state xt. The motivation of this is that in model predictive control, you are only doing control over a specific horizon, and what you're neglecting is that the state that you end up in has some cost associated with it. If you let the temperature go really high in a certain zone, well, there's gonna be a future cost because you have to cool that zone in the future. So adding in this terminal penalty function means that you can use a smaller look-ahead horizon and still account for that future cost. So we can write this as p theta of 1, and then when we go to multiple time steps, we have the same setup, just that we have p theta of h in the center now, and then we're introducing an offline training stage. So we have to learn these parameters theta that we use in that new terminal penalty cost function. The benefit over reinforcement learning shows up here. You're not starting from scratch. You're starting from a model and then just learning one correction to it, so it's much faster to train than reinforcement learning. Here I'm showing some results from an example of actually using each of these methods for building control. The plot on the left shows the error from each method, and the plot on the right shows the online optimization time, the time to solve this problem. The solid green line is reinforcement learning. You can see it doesn't depend on the look-ahead horizon h, and it's low. The error is low, and it solves the online, well, it doesn't have an online optimization problem. So it's very quick to actually run this. MPC, you can see that the error for a small look-ahead horizon is very small, and then as you increase that horizon, it decreases. But that comes with an increase in how long it takes to solve the online optimization problem. And MPC-L, you can see that the error starts off much lower. So while the online optimization time does increase with horizon, you can use a very small horizon and still have good accuracy. This chart here just shows a summary of each of the methods that I ran through. I'll leave it up here for a sec for you to each look at. But the key takeaway is this bottom line, MPC-L. You can see that for each of these kind of 4 challenges that I talked about, MPC-L addresses the challenge. And that column on the right shows that the caveat is that MPC-L becomes much harder to implement than the other methods. You need not only MPC, but also learning. I also just want to mention that these sorts of methods apply to many areas. I talked about building control. I'm also actively working on wind farm control, and there's a ton of other physics-based applications for these methods. Thank you.
All right, thank you very much. Okay, great. All right. And so our last speaker is Dhruv Patel. So he's a postdoctoral scholar in mechanical engineering. And he's going to talk about multi-fidelity modeling using machine learning. All right, thank you very much.
Thank you. Yeah, so today I'm going to talk about multi-fidelity modeling. So the general idea is I will start with what is multi-fidelity modeling, how and when it makes sense to use it, and then how one can leverage some of the recent developments in machine learning in the multi-fidelity setting to improve scientific computing. And then we'll end with giving a sneak peek into some of our ongoing efforts at ICME, where we are applying these ideas. So the ultimate objective of scientific computing is to model and analyze natural processes. Like our first speaker very nicely said, it could be as large as doing cosmology or small as particle physics. So we would like to simulate these natural processes, or we would like to simulate some engineering systems like flow around airplane and so on and so forth. And in all of this application, the workflow is pretty much the same. We start with some mathematical model. Most of the time, this model is not solvable, tractable on a on a pen and paper. So we use some kind of numerical discretization scheme to write down those equations in computers and solve it. And I like to classify or put this different methods on this plane of error versus cost. On the one hand, we have this high fidelity models, which have very accurate results with very low error, but with very high cost. And these could be traditional physics-based solvers. On the other hand, we could have this low fidelity models, which could give very low cost answers, but at a not so very accurate accuracy. So the question of multi-fidelity modeling is, can we combine the best of both the worlds? Can we combine this high fidelity and the low fidelity model in some smart way so that we can get reasonably accurate answer at a very low cost? And so one might ask, like, when it makes sense to use these ideas, right? For high fidelity models, it's obvious that one could use it when you are interested in very accurate answer. For low fidelity model, again, if you are budget constrained, you pick that. Then the question is when it makes sense to use this models, which lies somewhere in middle, neither here nor there. So there are broad classes of applications, which are sometimes called many query problems or outer loop applications, where you are repeatedly applying your forward model. So you have some input parameter, you feed in through your forward model, it produces certain output, and you try to optimize it. For example, in shape optimization, you are trying to figure out what is the optimal shape of that plane wing such that it gives the minimum drag. So in this application, you repeatedly apply your forward model, and this forward model could be very expensive, and so we would like to have a way to combine this high and low fidelity models. Similarly, in data assimilation, where you combine some of the observation with your model forecast to update the state of your PDE. Similarly, in the applications of inverse problems, where you are trying to infer some parameter given some observations. And in all of these applications, there is one outer loop going on, which repeatedly probes your forward model with different values of the input parameters. And so in this kind of applications, we would like a model which is reasonably accurate, but at the same time not so very expensive. And so in all of this outer loop applications, we can essentially replace the forward model with this higher fidelity, with this multi-fidelity model, where we have one high fidelity model combined with a hierarchy of different lower fidelity models. And so the question now is which lower fidelity model to use, right? So traditionally, people have used like simplified models where they essentially assume some simplified physics. So rather than solving on full 3D, they assume 2D problem, or they use coarser grid approximation, so approximation in some kind of simplified numerics. Or there is other class of projection-based methods like proper orthogonal decomposition, some reduced basis methods. And recently, data-driven methods have emerged as a very attractive alternative to develop this lower fidelity models. So these could be either supervised models like a deep operator network, where instead of learning function, you directly learn the operators, or could be unsupervised methods like physics-informed neural networks, or could be a method which preserves the physics by directly embedding physics in the neural network. And so now we are kind of getting in the realm of combining this physics and AI, and it's kind of nice to think about this two ends of a spectrum. On the one end, there are this traditional machine learning based methods which are purely data driven. On the other end, there are this traditionally physics based methods which are dominated by domain knowledge and not much data. And now we would like to combine and sit somewhere in the middle with some desired properties such that our hybrid model respects the underlying physics. It can extract missing information from this multi-fidelity modeling aspect. It can work with high-dimensional data, at the same time have a high computational efficiency, data efficiency, and a statistical efficiency. And it could give high accuracy with possibly reasonably convergence, with possibility of having convergence guarantees. So these are all the desired properties. And we would like to move towards that goal, and can hopefully provide confidence intervals so that we can have some kind of uncertainty in our answer as well. And so now the question is how to combine this lower fidelity surrogate models in our multi-fidelity settings. So there are multiple strategies for this. A class of problem, I would like to think of it as adaptation strategy, where you correct your low fidelity model with the output of from your high fidelity model. Or it could be online adaptation of your model reduction, so you use some kind of reduced basis as your low fidelity model, and in the online stage you adapt that basis. Or you could do some kind of efficient global optimization in that outer loop application. So this kind of falls into the adaptation, model adaptation category. Other could be the data fusion or model fusion category, where while training the data for your low fidelity model, you use both the low fidelity data as well as the high fidelity data coming from experiments or accurate simulations. Or there could be a partial replacement of some parts of your high fidelity model with the low fidelity model. Or one can also use ideas from classical statistics methods like control variates, where you use your low fidelity model to reduce the variance in the output of your probabilistic models. And finally, the third category of methods are filtering category, where one can use some kind of multi-stage strategy to sample from some target probability distribution, where you in one stage use low fidelity model to filter out the bad possible parameters, so that your high fidelity model only is used for important and accurate parameters. And similarly, one can use ideas from importance sampling and rejection samplings as well in this filtering category. And just to kind of give you a quick sneak peek into this final category for multi-stage sampling, so here at ICME, we are interested in this problem of figuring out what are the parameters which are responsible for ignition of a rocket engine. So this could be parameters like the laser location, laser intensity, geometry of the duct, and so on and so forth. So we would like to find out this whole probability distribution and this parameter space such that we can get a probability distribution corresponding to whether there was a successful ignition or not. And so we use this idea of filtering with this multi-fidelity modeling, where we use a lower fidelity model as a first stage filter, so that if the parameter is not very useful, it can be filtered out in the first stage at a very low cost. And one can use ideas from deep learning to construct this surrogate model, which is differentiable, which allow us to do more efficient sampling. And if that sample is accepted, then we move to the second stage, where a high fidelity model is used to correct the answer. So the key takeaways in this idea is to combine the best of both worlds, getting high fidelity models with computationally efficient low fidelity models. And I think machine learning provides excellent avenue because of its faster inference and automatic differentiation capability to play around with these ideas. Thank you.
Okay, great. Yeah, thank you very much for this presentation. All right, so let's move to the panel. So if the speakers want to come forward. So I have a bunch of questions that were sort of suggested by the presentation we just had. So I guess, one of the sort of central theme is this idea of, combining physics and data. So we have a large body of knowledge from, physical laws, relations, PDs, and so on. And I guess, initially there was a lot of excitement about machine learning, and let's forget about, the tyranny of grids and things like that. But I guess we're coming back to our senses and realizing that perhaps, the right approach is to combine these ideas and sort of, keep our knowledge and hard work in computational engineering and augment or improve that using data and technique from data science. So if some of you want to comment about that, this bridging between physics, equations, and data. So I don't know who wants to start.
Yeah, I can start from my end. Yeah.
Okay, sure.
Well, you tell me if I'm off the target with my answer. There are two major things that I see in high-energy physics that's been done. One is, maybe I start with this one. One is this thing you also mentioned, this physics-informed neural network type of things, which is in this case, for example, let's say you are learning some transformation by deep neural network or something that, from one space to another space, and you want to make sure that transformed space is also, say, equivariant. Not just invariant, but equivariant in that space for the transformation. In that case, you can do two things. One is you can kind of implicitly do this. For example, if you have some physics model, say in this case, let's say I have some physics model that says, if you transform into that space, and if the physics laws are valid, then it has to satisfy these rules. It could be maybe running your simulation on this in this transformed space, and then that output has to be invariant in this transformation. So in this case, you can do, and this is, I think, what I think the first idea about physics-informed neural network came up. You use neural network to transform one space on a space, and the output, you make sure it runs through, say, some simulations, some physics models, and make sure the output is still valid in that space. So that's one thing. We do that. So for example, if we try to learn inverse problem solving using neural network, we have the maybe forward simulation model and make sure the inverse model output, run the forward model, and make sure that it basically make the cycle consistency loop, for example. That's one thing. Another thing is, so that's the implicit surrogate model, using neural network, kind of giving a condition for the neural network to converge the solution where physics is respected. Another way is you just enforce the mathematical operations inside these models to respect some symmetry. So for example, you have a SU2 symmetry invariant normalizing flow, for example, that kind of stuff. In this case, you are focusing, okay, I want to, for example, maybe make sure that my convolutional neural network that's applied on a spherical surface, then it should respect the geodesics in the spherical surface, for example. Then you can just explicitly code that in your operations. So that's another way of doing it. So it's explicit way and implicit way is how I classify.
Okay, great. Yeah, thanks. Any other comments?
I think I mentioned this in my talk towards the end, but I wanted to highlight it a little more because of this question. When we think about using a purely machine learning approach, such as reinforcement learning, I think it's important to realize how frustrating and slow that training process can be. Just like looking at the results for building control, and in the papers I've read too for wind farm control, you can watch it just like explore in the dark, and it can't find a good region sometimes. And so you just see it trying all these bad options over and over. And when you add in some sort of model information, like in the hybrid method, at its best, it's really incredible how much better that learning process can be. It's starting from something that's pretty reasonable, and then instead of just staying there, like you would have in a purely model-based approach, you can see it get that little bit better that you still want. So I think in terms of the learning phase, you can definitely see how useful it can be to start from that model, but then not just stay there, add in the data through a learning approach.
Awesome, thanks. Yeah. Drew?
Yeah, I agree with both of you guys. I think in terms of like injecting this kind of physics, in addition to the two really good points you mentioned, like one is through, of course, the loss function, the implicit way, or building directly into the architecture through activations or some kind of normalization scheme. I think third way could be directly through the training data if you are in the supervised learning category. So it's like a training data bias. Another thing could be like your inductive bias where you build in that physics into your architecture, or third could be like your regularization or an implicit bias where you put it in the loss function. And depending upon application, one might be better than the other.
Okay, great. All right. Thank you. Yeah, thanks for these answers. So any questions from the audience?
So my question is this. The approaches that we have been discussing are sort of trying to connect physics and what we know from the physics to the data. One question that I have, are there opportunities to actually learn that what we know about the physics is wrong with some of these approaches? Because obviously we have been wrong before, right, with theories. So it's not that the physics necessarily is the correct physics that you put into the system. So I'm curious if, by going this route and building sort of most rigorous statistical methods that really assess perhaps correlation but also causation, maybe there are ways to sort out what are actually correct, what is correct about our modeling and our physical modeling versus what is actually data-driven. That might be, in some cases, more correct. So just... an easy question, but
sounds like a question for Kazuhiro with the physics of high energy physics and wrong models.
Yeah, I struggle to answer this question because it is something I often get asked, and I struggle to answer this question because I can easily say yes, we learned it, but the reason why I struggle is because there's no I haven't seen really systematic approach, something that's automatized to tell me your model is wrong. There are ways to. It's still the way that I see is it's still classical way. You project on some known axis of phase space, and then you see the shape is not matching with what you expect. But it's a manual process because you have to project on that space, and which means you cannot be like some arbitrary feature space on your network because I don't know that. Why do I look at this one specific feature out of million, for example? And so I don't think it's really automatized now. But there are things like, you mentioned, I didn't mention this in my talk, but anomaly detection technique, for example. So you specifically go look for something that your model failing. For example, if you just autoencoder and then you just look for the samples where your reconstruction is really bad and try to understand why. But again, this is not really automatic because, yes, it's bad. It basically tells me the information, this is not fitting with my expectation, but that's about it. It doesn't tell me why it doesn't fit. Right? So it's still a manual approach here. That's why I usually struggle to answer this because I actually want something to explain to me. And then I think we're pretty much talking about making general AI like human-like AI person that basically automatize this process of doing it because it's still a manual process. Now that being said, so I will give you some implicit answers. So there are certain cases where this can happen, where so I mentioned about the SUT invariant normalizing flow and stuff like that, right? And again, when you enforce certain symmetry and then analyze the data or the process, infer the data, infer the physics, it's a lot easier to see your model is wrong because there's only one assumption here in this case. Is this SUT invariant? If it's not invariant, then that's that. It's just that, again, so this can be useful when you're focusing on specific, it's saying you're projecting on a specific axis, right? And then if it's wrong, okay, so it tells you something about it. So yeah, so again, I think basically I come back to this point that I haven't seen generalized approach on all possible variables out there. Like how can I find which variable is wrong in a systematic manner, and even more reason it. Like why is this variable wrong, and so therefore the secondary wrong variable is a little bit wrong, right? And why this is a little bit wrong, that this one's really wrong because there's some physics explanation between these two. There's a correlation, right? There's no automated way of getting this explanation. So maybe that's just maybe dream, but yeah, it's been useful. I shouldn't downplay the machine learning and the statistical inference techniques in the recent years. It's been very helpful, but it's not. I think it's not there yet to say, yes, we have a solution.
Yeah, at some level, data science seems pretty tough in high energy physics because you have some people who try to develop new models purely from theory, from certain symmetries or certain just like mathematical insights and get to derive some laws. So coming from here, we're kind of coming from the opposite angle, just data. So yeah. Okay. Any other? Do you guys want to comment or?
No, I think I pretty much agree with what you said. Like I have seen some papers where they use kind of this ideas from symbolic machine learning and regression, but again, like you are putting in a prior information, like my underlying law will have this particular structure, and of course it will figure out the coefficients. But yeah, I'm not aware about any fully automated machine learning techniques yet.
I have maybe a slightly more optimistic view. I agree that if we're trying to go from like very start to very end, learn everything to describe the system, it's pretty challenging to do that. Although if I remember right, I think your group maybe had some work on learning partial differential equations themselves. And I think while that's a very new topic, there is some hope that in the future you could do that. And if you learn a partial differential equation for some more complicated physical system that's different than what you already came up with, that would raise some pretty clear questions about did we really get the right PDE to begin with? So I think that's early work, but there's definitely a lot of promise there. I think also if we break down the problem into smaller parts, we've seen machine learning in a variety of fields be useful in showing us that some of our understanding so far has been wrong. I think in medicine, in terms of diagnosing diseases, machine learning has been used to look at imaging, for example, of the body, and to point out that certain features that doctors haven't been looking at so far actually have a strong correlation to a disease. And that then leads doctors to change their practices. Previously, they said, oh, only the the BMI is important in predicting this disease. In reality, it turns out that, say, the fat that you have specifically around the liver might be more important than just BMI. So while that's maybe not changing a physical model, it is really changing our understanding. And I think that applies to a lot of systems. Also, when you think about parameters, that's perhaps a very simple example of where you could use data and machine learning, but certainly we have physical systems where you have some parameter like a power, you say. When we talk about wind farm power, that relates to some constant with, say, a power of 2, and then one looks at the data, and you could use machine learning in this case to realize maybe that power shouldn't be 2, but it should be 2.7 or some other value. So I think there's a lot of opportunities to use machine learning to learn part of this, part of what a model should be, and maybe we can work towards more and more of that model being able to validate our understanding.
Okay, great. Yeah, thanks. Okay, all right, thanks. Yeah, sure.
Yeah, we are about ready to stop and start the poster session and have a break. So thank you for all these interesting talks. Just as a last word, I'm very excited about human level AI, but you can imagine that the human still makes a difference. An Einstein level AI versus somebody else A-level AI will still make a difference. So I think that's certainly a testament to algorithms, but also some more about power of induction and abilities to really think about problems in a different way. So anyway, just to finish off, I want to thank you all for attending, for participating in the sessions. This has been a pleasure to finally be back in person. We've had some glitches. We're still not completely out of the woods, as you can see. So unfortunately, for some of the speakers and moderators, this has been not completely smooth, but I'm happy again to see all of you here. So without further ado, I think I'll close the formal session. I want to, again, thank you all for being here, and thank you again for participating in Expo this year. Thank you.